slides. I have to use my little baby stylus here. And I think this one only has an hour of charge, so we'll see how this goes. I charge it on the side of this thing, but we'll kind of go on from there. All right, so coming in today, there was this question waiting for you on the Socrative app, as there always will be a question waiting for you on the app when you come in. Before we get to that, though, let's go ahead and take a look at the announcements for today. Again, I only do this for the first 2 weeks, and after the first 2 weeks, I assume you will act as responsible college students and will take charge of your own due dates and such. But have these reminders. First of all, you have the email that's due today, and it's not any old email. Where do you find the instructions for the email? All right, back page of your syllabus. Then once you complete, and some of you have not seen that there's actually a subject line you're supposed to be using, and there's supposed to be stuff you're putting in there, so it's not any old email. There are requirements for it. Chapter 2 extra credit problems, some were due last night, Part A and Part B due tomorrow. Math and Chemistry homework quiz for Chapter 2 is due on Monday. Any questions on the syllabus? Anybody need a copy of the syllabus? Okay. Required safety training was in lab last week. That must be completed before you participate in lab activities. There's a pre-lab quiz on D2L that must be completed with a minimum score of 2 out of 3 before participating in lab. I know half of you had lab yesterday. The other half have lab after class today, I believe at 10 o'clock. You do need to complete that pre-lab quiz before you participate in lab. If you're having trouble with your access to Mastering Chemistry, please understand that there's a 14-day free temporary access that's available. Any questions on that? Okay, and then the Socrative Student app. And then we do have an element quiz. We'll talk about this in more detail on Tuesday of next week. I do want to give you the heads up. Which elements should you be studying for the element quiz? Not all of them. Which ones? The ones in gray, exactly. And there's 2 things you should know about the ones in gray. You should know the name with correct spelling, and then you should know the chemical symbol with the proper capitalization or case. Remember that the first letter is always capitalized, the second letter is always lowercase. Okay, and that is going to be on D2L. I will give you more details about that on Tuesday. It will unlock for you next Tuesday at 9:30, right after this class. So I don't even know if you can see it on D2L right now. Can you? Yeah, but it will not unlock until 9:30 next week after we've gone through a little bit more specifics on it. Okay, let's take a look at our Socrative app question as you came in here today. A tank of gas on a medium-sized car holds 15 gallons. This is the same as, if we check out the answers here, looks like we have a variety. The correct response here is 57. 57. And that is with the correct number of significant figures. If you need a calculator, I forgot to do those, come up and get your calculator now if you need one with your collateral. Okay, let's do just a very, very quick check here on how we would go about doing this and why we have the sig figs the way we do. First of all, we've got, oh cool. First of all, we have 15 gallons. And we were looking for the number of liters. So we need to go to our conversion sheet. And if we look at our conversion sheet, we find a conversion right here that says every 1 gallon we have 3.785 liters. How many significant figures is this worth right here? 4. And of course that's given right up above. So then we need to place the conversion in here in such a way that the units cancel. The units that are going to go on the bottom would be the 1 gallon. And on top would put in the 3.785 liters. Once we have this all set up, of course, units of gallons will cancel out. We multiply this through, And I don't know, you probably get 56 points something, whatever. So then you need to round it off to how many sig figs? 2. Because this number here has 2 significant figures. This conversion has 4. The fewest of 2 and 4 is 2, which means we round it off to 2, and that would be the 57 liters. Any questions? Okay, let's do the next one here. Let's convert 65 miles per hour to SI units. Let's convert 65 miles per hour to SI units. Well, let's go back to what SI units are. If we look, first of all, at 65 miles per hour, it looks like we're looking at a speed which has in the numerator a length and the denominator a time. So what is the SI unit of length? It's the meter. And what is the SI unit of time? The second. So that means we are going to be converting. If it's not specified, you need to know what your SI units are. So we are converting specifically to units of meters per second. So now that we have that, we have our 65 miles per hour. And my recommendation to you, here's how you wind up with those mistakes on these problems, is if you write the units side by side. If we think about a numerator and denominator, the units of miles belong where? On the top. And the hours belong on the bottom. And we're going to convert these to units of meters per second, and meters on the top, seconds on the bottom. Now this one's going to require 3 or 4 conversions. Let's go ahead, work here for a few minutes, and see if you can come up with a conversion. You need to know your conversions that are provided on the sheet there, and you should also know the units that you're expected to memorize, the metric to metric ones. You would have had that done by today. Work together on these, please. If you don't know where to begin, don't be staring out in blank space. Talk to somebody that looks like they know what they're doing.
It's $1,000. I had it on here.
All right, let's go through and look at some possible solutions. I understand that some of you probably aren't done. That's because, at least the saying was, when I was growing up, there's many ways to skin a dead cat. All right, so there's several ways this could be done. There's not necessarily one right way. Let's talk about one way. What's one conversion we could do to start this off with?
You have to do kilometers because
Convert to kilometers?
Yeah,
Okay.
kilometers and miles.
Kilometers and miles. So if we did kilometers and miles, where is miles going to go?
On the bottom.
And where would kilometers go?
On the top.
Okay. How many started a different way? Instead of going from miles to kilometers, went miles to something else? Yes. Okay, feet to meters? Yeah. Before that? Yeah, miles to feet. So where would miles go? On the bottom. Where would feet go? On the top. So now, let's say we're doing the one on the top. We went miles to kilometers. We go to our conversion sheet. Here's our miles to kilometers right here. 1 mile is 1.609 kilometers. We can come back here and put in 1 mile is 1.609 kilometers. Now, if we were doing miles to feet, you could have done that by doing this length conversion right here. 1 mile is 5,285 feet. If you did that, 1 mile is 5,280 feet. In either case, units of miles would cancel out. And if you stop the calculation at this point, you would have units of kilometers per hour or feet per hour. So now, if we're doing the top one, after kilometers, what would the next conversion be?
Meters.
Meters where?
On top.
On top, and on the bottom?
Bottom, kilometers.
Kilometers. So now this is not one that you're going to find on your conversion sheet because this is metric to metric. So what you need to do is you need to remember the conversion for kilo. Kilo means 1,000. So if I were to ask you to run, would you prefer to run a meter or a kilometer?
A meter.
Probably a meter, most of us. All right. So if we want to put the number 1,000 in, the 1,000 is going to go where?
On top.
On the top there. There's 1,000 of the smaller unit in one of the larger unit. At this point, units of kilometers cancel out. Now, if you did the one on the bottom, you have feet. What was the next conversion we did? What's the next conversion?
Meters of feet.
All right. So what would we put on the bottom? Feet. And on the top, we'd put in meters. And here you have this conversion right there. 1 meter is 3.281 feet. And at this point then, units of feet would cancel out. So now again we stop. It looks like we have meters per hour as our units on each one of these. So now we have the correct numerator. We wanted to get to meters, which is where we're at. Now we need to convert that denominator. So how do we change hours? On the top we put in how many hours? 1 hour. And on the bottom?
36.
Okay, I hear 3,600 seconds. Let's do that one down below. Or in 1 hour we have how many minutes?
60.
60 minutes. Okay, and at this point then units of hours would cancel out. And then if we took it one more step, on the top would put in 1 minute, and on the bottom 60 seconds. And again, units of minutes will cancel out. In this case, hours would cancel. Now, one of the things I would caution you about when you jump from hours to seconds, probably the biggest mistake I see, and people do it all the time, they say in 1 hour we have 60 seconds. Okay? So I just need to pay attention to that. But now, these are both set up. If you want to calculate this, remember the way that we do this, if we want to do it efficiently, is we multiply together all of the values that appear in the numerator and divide by each one of the values that appear in the denominator. So if I was doing this on my calculator, it would look something like this. And let's see if I can zoom in on this at all. There we go. So I would take 65, I'd multiply it by 1.609, multiply it again by 1,000, I'd divide it by 60, and I'd divide it by 60 again. Because again, the 60 appears in the denominator twice, so we need to divide by 60 each time. When we do so, we wind up with an answer of 29.05, etc. If we did the second setup, what do we get when we do the second setup? Do we also get 29, or do we get a different answer? Come on, this darn thing is slow. So the first one's 29, the second one is also going to be 29. So again, it doesn't matter which way you do it. Each one of them is set up correctly, but each one of these should be rounded off to 2 significant figures, because this number here has 2 significant figures. This is an exact conversion. So if we go back to our exact conversions have how many sig figs? Infinite number of sig figs. And then we have 4 sig figs and an infinite number. So the fewest of those would be 2. We round our answer off here to 2 significant figures. So any questions with these? Any questions? All right. Next up, we are going to go on to a new topic here. Let's say that I have a pound of lead and a pound of feathers. And we make the statement, a pound of lead is heavier than a pound of feathers. Is this statement true or false? We'll get our answers locked in. We'll count down. 5, 4, 3, 2, 1. Okay. Well, this is definitely a true statement. If it weighs a pound, it weighs a pound. They both have the same weight. Neither one is heavier than the other. How is it the two differ from each other?
They have more feathers will equal.
When you say more feathers, what do you mean by more feathers?
You're going to need a whole lot more feathers than you are lead.
What do you mean by a whole lot more?
Quantity.
Well, it's a pound is a pound.
There's no way that a feather is going to be a pound. You have to have.
What is the difference?
The quantity. That's what I said.
I would say the quantity. The density is going to be different. Exactly. The density is going to be different. What else is going to be different about them? You have to be careful when you talk about the quantity, because quantity, that means you're assigning a numeric value to it. 1 pound is 1 pound. So you're not specifying what the quantity is. If you're specifying a quantity, you need to know which quantity. So density is 1. What's another thing that's different about the two? The mass is not any different. What is different?
The material.
If you saw them, you saw a pound of lead, and you saw a pound of feathers. What's going to be the difference when you looked at them? Not the quantity. The volume is going to be different. Exactly, the volume. The amount of space that they take up. That's not the quantity. The quantity is when we assign a numeric value to something. We assign a numeric value. It could be volume, it could be mass, it could be density, it could be any one of those things. So it's going to be the volume. So what we're going to head into next is going to be the density. And we define the density like this. We define the density as being the mass per unit of volume. Now we're going to see a ton of definitions this semester. And when we look at definitions, we should be able to take a definition and from that definition write out a mathematical equation. As long as we know what some words mean. Mathematically, the word per means to divide. Exactly. Means to divide. So if we came back here and we're talking about miles per hour, and we were to calculate it, if you wanted to calculate the number of miles per hour, you take the number of miles and divide by the number of hours. Or if you wanted meters per second, you would take the number of meters and divide it by the number of seconds. We say miles per hour or meters per second. That means to divide. So if we wanted to write out an equation then, let's write out an equation with this definition. Density is equal to mass over volume. Good. Mass divided by volume, which we then write as D is equal to M over V. And this is one of those equations we need to know in here. So now let's say that I look at this block of wood. And I've had this block of wood with me every year since I started teaching. I've dropped it a few times and it's cracked, and some things have chipped off. Let's just assume it's a perfect block of wood. If I want to find the density of this block of wood, what would I need to do to it?
Measure.
What would I need?
Weigh it.
I need to weigh it. Okay? So let's go ahead and measure its density. So I brought out here a scale to which we can do that. And we'll plop this onto the scale so you can see. And we'll slide this into the view right here. So there we go. And let's zero it. And we'll put this on. Let's record this mass. It looks like we have a mass of 233.66 grams. So the density is equal to 233.66 grams. And then, what else do we need for this block of wood? We need the volume. And how can we find the volume?
Measure it. Measure it.
How would we measure it? Be specific.
In fluid.
Length times width times height. That would be one way. Another way might be to do a way that you'll be doing in lab next week, and that's to use a technique called water displacement. And so we could push it underneath the water, maybe just point it down like that and find out how much the water level goes up when we do that. So we need length, width, and height. So I'll go ahead and measure these here for you. let's start first of all. I had a ruler here somewhere. There we go. And I'm going to do this very quickly because it's got shade corners and everything. So we're going to estimate to the nearest tenth. Looks like for the length, we've got 16.6 centimeters. And again, remember, volume is length times width times height. Then we'll have a width that we'll record as 8.8 centimeters. And then we'll have a height, which appears to be about 3.7 centimeters. So again, our formula is D is equal to M over V. And the bottom we put in that volume. And part of the reason why I'm not calculating the volume up front is I'm trying to avoid calculation errors. We don't want to do any rounding until our final answer. In fact, some of you, when you do your Master in Chemistry, you're going to say, well, my answer is different than what was shown in the back of the book, or different than what's shown in Master in Chemistry. And that's because you're stopping and you're rounding off in the middle and then calculating again. The best practice is not to do any rounding until the final answer. So if I were to do this one on my calculator, here's how I would do it. I am going to take 233.66. I'm going to divide this by 16.6. I'm going to divide it again by 8.8 and divide it again by 3.7. And I think part of my job here is to teach you keystroke efficient ways to do things, because of course it comes to exam time, you're going to want to save time. And the reason why these aren't multiplication down here is because each one of these values appears in the denominator. So whenever you're multiplying by fractions, anything that appears in the denominator is a value by which you should divide. And now if we calculate this out, I get 0.4323, etc. How many significant figures should this answer have?
4.
I hear 1, 2, 3, 4, 5.
Yeah.
There should just be 2, because the 8.8 has 2 sig figs, and 3.7 has 2 sig figs. So we find the value that has the fewest significant figures. Our answer should be rounded off, so it contains the same number of significant figures as the measurement with the fewest. And so this answer then is going to be 0.43. And the units now, what are the units in the numerator?
It's grams
Per centimeter
squared.
cubed. Per centimeter cubed. Because centimeters times centimeters times centimeters gives you cubic centimeters. This would be the result. Or, we learned the other day that a cubic centimeter is the same as which other unit? Which one?
No, not a centimeter. That'd be
cc's, or what's another name for it? Milliliters, exactly. So it'd be 0.43 grams per milliliter. So if you wrote out your answer with either one of these units, that would be okay. This, of course, is the way that you calculate it. But as long as you know that a milliliter and a cubic centimeter are the same thing, this would be an acceptable way to write that answer out. And whenever you write out the density, the units must have a mass value in the numerator and a volume unit in the denominator. So densities always have a mass per unit, mass per volume unit to represent it. And in your text, I don't have mine with here at the moment, but in your text there is a table that shows the density of a number of different substances. And anybody happen to have their text with here today? So we can look, so you know the reference. Because you'll need to use this on your Master in Chemistry and your end of chapter problems. So let's see. Density is discussed in section 10. It appears there's a table of densities on page 40. So page 40, you'll find a table of densities shown in the upper left-hand corner of that table. And so in cases where we need it, that's where it'll be found. You'll see that the table there is given in units of grams per milliliter or grams per cubic centimeter. Now, when we calculate answers, one thing I've not prompted you to do yet is you should always ask yourself if an answer makes sense. And you should ask yourself, does this answer make sense? And you might say, I have no idea if it makes sense. How would I know if it makes sense or not? Well, if I took this piece of wood and went out to the river out there and tossed it out in the river, what would happen to it?
It floats.
It would float. And if it floats, what does that mean about its density? It's less dense than water. It's not lighter than water, it is less dense than water. So it would float on the top. And so it would be helpful to know then what the density of water is. Anybody have any idea what that value is for water? 1. When we say 1, it has to be accompanied by units. In the case of water, the density of water is 1 gram per milliliter. Okay, so when you learn that value of 1, the density of water is 1 gram per milliliter. Turns out that that is at a temperature of 3.97 degrees Celsius, which is where water has its maximum density. Density is something that changes with temperature, and that really is how hot air balloons work. We heat that air up, and that changes the density of the air that's in the space above the basket. And so when that density changes, then that causes the hot air balloon to lift. Okay, so again, compare it to 1, and in this case it's less than 1, so it should make sense. It would float. If you calculate a density and it's something like 5,000 grams per milliliter, right away that should tell you you've done something wrong. There's nothing here on the surface of the earth that is that dense. In fact, the most dense element that there is the element osmium. And osmium has a density of about 23 grams per milliliter. So anything that's more than 22 or 23 should be an answer that does not make any sense, because again, the most dense substance there is here on the earth is the element osmium. And you'll find out that when I get to exams, I try to write out questions where you can ask yourself, does this answer make sense or not? It might be to calculate the weight of a baby in pounds. If you calculate a 10,000 pound baby, it probably doesn't make sense. Or if you find a snail that travels at the speed of light, probably doesn't make sense. All right? So when you calculate your answers, you should always ask yourself, does it make sense? And don't worry, we'll have people that will have snails traveling at the speed of light in here, and some of you have 10,000 babies, or you'll give doses of antibiotics of like about 5 million tablets in a day. Okay? It doesn't make sense. If it doesn't make sense, you redo it. You try to figure out what it is that you're doing wrong. Okay, next up, let's look at another question. Now this one here, we're going to write out some information. We have an empty graduated cylinder. Somewhere here, there we go. An empty graduated cylinder. Has a mass of, and we'll weigh this in just a bit, blank grams. And then we're going to fill it up with some water, so we'll say blank milliliters of water is added to the graduated cylinder. And then we'd like to know, what is the combined mass of the cylinder and water? So now this is going to be a lot like some problems you'll be encountering here as you go through the stuff in the end of chapter 2, and this will be like some stuff you'll be doing in your lab next week. Let's go ahead and fill in some blanks on here, and let's find the mass of this graduated cylinder. I got the balance zeroed out. We'll place the graduated cylinder onto the balance. Looks like we have a mass of 100.44 grams. So I'm going to write that in. I know you can't see it right now, but 100.44. And then I'll place some water into the graduated cylinder. And we'll place it back onto the balance. Except not quite yet. I'm going to read the volume on this graduated cylinder, and we can record this. It appears to be about 55.2 milliliters. About 55.2 milliliters. So next up, we want to try to figure out what to do with this. So let's kind of write out a map of some of the things we do know. Do we know the mass of the water that's in the cylinder?
Yes.
Do we know the mass? No, we don't. We want to know at the end what the combined mass of the cylinder and water is, but we don't know what the mass, we didn't weigh it out. What do we know about the water? Its volume. So what we do know about the water is we know the volume of the water. We know that the volume of the water, and so I'll write it like this, the volume of the water is 55.2 milliliters. Now if we kind of put this together in a little map, we could say that the mass of the water plus the mass of the cylinder is going to give you the total mass. And so this isn't a formula you're going to look up anywhere when you think about it. These are just my abbreviations. We sum together the mass of the water and the mass of the cylinder. This is going to give us the total, and that is what we're looking for over here. So we're looking for what that total mass is. Now at this point, which one of these values do we know? We know the mass of the cylinder. All right. So the mass of the cylinder we know to be how much? 100.44 grams. Now we don't know the mass of the water yet, but we should be able to figure out the mass of the water from its volume. And that is because if we look at the density formula, the density tells us that density is equal to mass divided by volume. And so we know the volume of the water. The density of the water we know is about 1. I'm actually going to give you a more specific value here. The density of the water, it turns out, we're at about 23 degrees Celsius right now. So the density of the water is actually 0.997 grams per milliliter at a temperature of 23 degrees Celsius. Okay, so I'm telling you what this is right now. This is something that you would need to look up from a source of values if it was available to you in a problem or whatever. I've done the looking up for you. It's actually stored up here in my head. Okay, so we know the density is this value. So now, if we know the density and we know the volume, we should be able to use the density and the volume to calculate the mass. So we need to get mass by itself. To get mass by itself, what do we need to do to each side of this equation right here? Multiply each side by? Well, let's not jump ahead. Don't put in numbers yet. Multiply each side by the volume. And the whole objective of doing that is to get rid of V on this side. It tells us mass is equal to volume times density. If you're jumping ahead and just plugging in numbers, you risk the chance of having calculation errors. I know, because I see it all the time. So this tells us then that the mass is going to be equal to the volume times the density. So now we should be able to plug this in. We have the 55.2 milliliters up here. We have the density, which is 0.997 grams per milliliter. What happens to the units at this point? They cancel out. Which cancels out specifically? Milliliters cancel. So we'll take the 55.2, multiply it by 0.997, and we get 55.034. How many significant figures should this answer have? 3. So we'd round this answer off to be 55.0. The label would be grams. Now remember, this is the mass of which stuff? The water. So now that we know the mass of the water, we can come back up here, put in the mass of the water as 55.0 grams. And now we want to sum these two together. Once we sum these two together, we are going to get 155 point. How should we round this off? Now when we add and subtract, we look at decimal places. So which of these has the fewest decimal places? The first one. So how many decimal places should this answer have? 1. So we'd round this off to 155.4. The label would be grams. So this is the answer that we'd expect, 155.4. So now if we want to know what this is, what we can do is we come back to this here, see how well we did. We place this onto the balance, and it's reading as 155.66. Is that an acceptable value?
Yeah, because isn't the last one uncertain?
The last digit is uncertain, so that means which place should be uncertain in this calculation?
The 6.
The 10th place, exactly. The 10th place should be the uncertain digit. We showed that the 10th place was uncertain right back here. And so since the 10th place is uncertain, we'd expect to see some variation here in the 10th place. Just like we did, we saw 155.66, and we saw that the uncertainty was indeed in the 10th place. Okay, any questions with this? Okay, now, there could be some problems that you'll be doing in your homework where you have to calculate volume. If you have to get volume, let's go back to our original formula. D is equal to m over v. Let's see how we'd go about calculating the volume. We need to get v by itself. Now to get v by itself, v can't be in the denominator, v has to be in the numerator. So to do this one, we need to get v up in the numerator, which means we have to multiply each side by v. If we multiply each side by v, v here is going to cancel out. We find that m is equal to v times d. Then to get v by itself over here, we need to divide each side by d. Once we divide each side by d, d here winds up canceling out. Once d cancels out, that tells us that v is going to be equal to m over d. And this would be the way that you'd calculate the volume. V is equal to m over d. Now, of course, I can listen just by your responses here that some of us are algebra challenged. If you're algebra challenged, we can make what's called the density pie. And here's what the density pie looks like. We're going to make the pie, let's try to do it better, there we go. And in the pie, we're going to cut it in half, and we're going to divide the bottom section into quarters. And then you're going to give me on top the biggest. M for me. Okay, give me the biggest. And then the rest of you, V and D, get the smaller pieces. And so here's how the density pie works. Let's say that you want to calculate the density. Whichever one you want to calculate, you cover it up. I'm going to calculate D. D is equal to m over v. If you want to calculate v, cover it up.
M over D.
M over d. If you want to calculate m, cover it up.
V times.
V times d.
That's
Any questions? This is called a mnemonic. Okay, mnemonics are memory aids. Okay, first memory aid I remember learning is "Every good boy does fine," which of course is music. It's the lines on the treble clef. All right. And then if you learn face, F-A-C-E, then you learn the spaces in the treble clef. So I have all sorts of these. I'm going to be giving all sorts of mnemonics this semester. This is called the density pi. Just remember to give me, M, the biggest, and put yourself on top, and you'll have the density formula. Any question? All right. Next up, I passed out a handout, and on that handout looks something like this. Anybody not get a copy? All right. Now notice that this handout has two sides. This handout has two sides. It also has dates on it. Notice the date on the flip side. The date on the flip side is not today. The date on the flip side is next week, next Tuesday. Don't lose this. We're going to use it again. I've made just enough copies for my two classes. Don't lose it. We're going to use the front side today and the flip side again on Tuesday of next week. We're moving on to Chapter 3. And in Chapter 3, we are going to be looking at chemical change and physical change. This is the part of chemistry that got me interested in chemistry when I was a student. I started college as a math and music major, and I wound up in chemistry of all things. All right? And it was chemical change, physical change, once we started doing this real chemistry stuff, that I got really excited in chemistry. So what I'm going to do here, first of all, is we're going to give some definitions. And once we see the definitions, I have a bunch of demos we're going to do today. We're going to classify them as chemical changes or physical changes. So we'll start by giving some definitions. For the first one, a physical change. A physical change, we say, is a change in which no new chemicals are formed. So this here is a change in which no new chemicals are formed. And a chemical change, this here is a change in which new chemicals are formed. So physical change is one which there's no new chemicals formed. Chemical change is one which there are new chemicals are formed. And so when we look at these here today, you want to ask yourself, are we looking at something which there are new chemicals or there are not new chemicals? And you ask yourself that every time, whether there are new chemicals or are not new chemicals. And so we're going to complete these then. And as we complete them, we are going to have some questions that will show up here on the Socrative app. And these will show up in order. You're going to make your guesses and such as to what happens. So we'll start here, though, by looking at the first demo. And the first one, I am going to start with some calcium chloride and sodium carbonate. Calcium chloride and sodium carbonate. And so I'll put the two chemicals in. I'm actually going to swap out my balance here for a different one so we can see it more conceptually. This will take me just a couple seconds to get out. Here's an old-fashioned balance, but this is one that helps us determine what's going on conceptually. So I'm going to start, first of all, by placing these two solutions onto the balance, and we're going to record their mass. And of course, if we've not worked one of these before, the idea is that we want to get them so that they're swinging back and forth the same amount. Looks like I'll need to add on a weight over here, and we'll add on a little bit more. And what we try to get it to do is we try to get it to swing back and forth equal amounts on each side, which it looks like I've come pretty close to doing here. Whoops. Kind of doing this a little bit too fast. But now if we were to write this mass down, and I'm still not quite there, and it looks like now I probably am. So now we have a mass of 213.7 grams. And the 213.7 grams is the combined mass of these two solutions. Now what I'm going to do to these two solutions here is I'm going to pour them together and we'll watch what happens. So again, this is calcium chloride and sodium carbonate. I'm going to pour one with the other now. We see how it's turned white and cloudy. This here is called a precipitate. Whenever you mix two clear solutions together and it turns cloudy, that's called a precipitate. And so we come back to our statement here. Would say solutions of calcium chloride and sodium carbonate are mixed, yielding a white precipitate. And the white gives a descriptor as to its color. You can decide now, don't yell it out. We're going to put it on the app. You can talk to the neighbor. Do you think this is a chemical change or physical change? That's the first one. So again, write down your prediction. I don't have it up there on the screen yet. Do you think this is a chemical change or physical change? You write down your prediction. You're going to get a chance to answer it. The next thing we're going to look at here is what do you think has happened to the mass? And I think that's the next question on here. What do you think has happened to the mass? Do you think it has increased, decreased, or stayed the same? Now before I popped it up on the Socratic app, the word precipitate means literally to fall out. So now when you heard a precipitate or precipitation before, where have you heard that?
Rain.
In the weather, like rain or snow or sleet, and that's stuff that's literally falling out of the sky. Okay? So in this case, we have formed a precipitate. A precipitate is a solid, and as I let this sit here longer, one of the things that we're going to notice is that this precipitate is going to settle to the bottom. So we call that a falling out. So now the question is, and before I place it on here, there we go. Do you think the measured mass in the balance is going to increase, decrease, or stay the same? And always feel free to talk with a neighbor, because nobody likes to be wrong. Let's get your answers locked in. We'll give you about 15 seconds. And we'll count down. 5, 4, 3, 2, 1. Of course, the best way, rather than just putting it up on the Socratic app, is to actually test it. And if we place these two on here, and now look at the swing back and forth, it appears that the mass has stayed the same. Stays the same. Now that should not be a mystery, because I think our next question here is, and I'll tell us why. When we look at the solution, and they mix together yield a white precipitate, do you think, based on our definition, is this a chemical change or a physical change? And we'll get our answers locked in, please. We'll count down. 5, 4, 3, 2, 1. This here is a chemical change. Now, first of all, you want to write down some evidence. This is somewhere on your own space, on the side in your notebook. one piece of evidence that the chemical change has taken place. There's actually two pieces of evidence here. One is the formation of a precipitate. Whenever you see the formation of a precipitate occur, when you mix two clear solutions together, or transparent solutions, you get a precipitate. That's going to tell you that a chemical change has taken place. There's a second piece of evidence that a chemical change has taken place in here, and that is a change in color. Exactly, a change in color. If you see a change in color will indicate to you that a chemical change has taken place. So again, those are our first two pieces of evidence. If you see a color change, it tells you a chemical change has taken place. If you see the formation of precipitate, a chemical change has taken place. Now, the other thing here that we observed is something we refer to as the law of conservation of matter. The law of conservation of matter. And the law of conservation of matter says this. It says matter can neither be created nor destroyed as a result of a chemical change. Okay, so this was a chemical change that took place right here. And basically you can kind of think of it as if we had a bag of nuts and bolts. And the nuts and bolts were not connected to each other. If we had a bag of nuts and bolts, they weren't connected to each other, and then we took the nuts and bolts and connected them to each other and reweighed that bag, what would happen to its weight? It would stay the same. That's kind of like what chemical reactions are like. You can think about the atoms as being nuts and bolts. Just being kind of separated from each other and then being joined together. Or being joined together and taking them apart. As long as that's what we're doing, we're not changing the number of atoms in here. I didn't add any atoms to it. I didn't take any atoms away. So if I didn't add any atoms to this or take any away, then this mass should stay the same. Okay? Any questions? All right. Demo number 2. How many done baking soda and vinegar before? Yeah, you've all done that one. All right. We do some baking soda and vinegar. I'm going to go ahead and put some vinegar into this one here. And I'm going to put some baking soda into this one here. And again, we are going to place these onto the balance and weigh them out. And this one I probably don't need this weight on there. So we'll slide it down and check this out. Looks like I need just a little bit more on this. And slow down here a bit. All right. So now it's kind of swinging back and forth. It looks like we have probably about the right amount. There we go. So now what I'm going to do, whoops, it's the wrong one. How about that? Why didn't you tell me? We'll put it back on there. I need this mass back on. I got a little out of shape being on my long break. Don't worry, that's just an excuse. I'm like that all the time. I'm getting old and feeble. You know, my parents told me all the time that you start forgetting everything when I was growing up, and I didn't believe them. Well, then I got old myself, and gosh damn it, my parents were right. Okay. All right, so here we go. 247.4. 247.4. And that, of course, is the combined mass of these two. Now, what I'm going to do with this is I'm going to pour the baking soda into the vinegar. I'm going to do this slowly. I don't want to lose any, and I don't want anything to spill over. So of course, if you've done this one before, yeah, if we did it really fast, we get a big old volcano. I'm going to do it slow, because I don't want it to go over the top, and we kind of lose the point of this. So now I'm going to go back and place these onto the balance and remeasure the mass. And so now, of course, you've seen I haven't dropped anything. I'm going to come back here onto the balance and remeasure its mass. Now, what's the fun in doing that unless you make your own prediction as to what's going to happen? So now, baking soda and vinegar are mixed to yield carbon dioxide gas, which of course we can fill in the blank. The mass measured on the balance will I'm going to have to rewrite these notes later because I'm not used to using this small stylus. I don't know what's going on. It's kind of funky, huh? Alright, well, I'll get a new battery on my other stylus. So let's go ahead and check out the responses. Let's get your answers locked in, please. Heck, I can't even touch this now. Can I tap with my finger? There we go. I'm going to have to go to my finger. All right, we'll pop these on here, see what happens. And once we place them onto here, what has happened to the mass? If this side is now up higher than this side over here, that must mean that the mass had decreased. It had decreased. Now, is this disproving the law of conservation of matter?
Yes.
No. What it is doing is actually supporting the law of conservation of matter. It supports the idea that gases have mass. Because if we made a gas, the gas is no longer in here. Where did it go? Into the air. All right. Now, there is a way that we could have shown that mass is conserved with this reaction. How could we have shown that it was conserved? We had a lid, and not just any old lid. It'd have to be a tight seal. Exactly. Have to put a tight seal in there, and if I could seal it up tightly so none of the gas would escape, we would then find that mass was indeed conserved. So we go on to the next question. Baking soda and vinegar mixed to yield carbon dioxide gas. This is an example of We'll get answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. It is a chemical change. We ever mix chemicals together and we see that a gas forms, that is another piece of evidence for a chemical change. So it is a chemical change. Next up, I am going to heat some sugar. So somewhere over here I have some sugar, and I'm going to start up the burner. We'll go ahead and put some sugar into this test tube here. A little bit more than that. There we go. Pop that in. And now we'll do this so you can watch on the screen. There we go. Here's our sugar. We'll put the sugar over the top of the burner. And notice now as we start heating it, it's starting to bubble. Can you see what else is happening to it? It's turning brown. All right. So now, and then you'll see some condensation on the top of the test tube. We're heating sugar until it turns brown. You can fill in the blank. We're heating sugar until it turns brown. Is this an example of a chemical change or a physical change? And we'll get our answers locked in on this one. We'll count down. 5, 4, 3, 2, 1. This is an example of a chemical change. It's one of the things we already mentioned already. What did we see happen there? Color change. If it's a color change, it tells us there is a chemical change that has taken place. In fact, if I walked around, some of you don't even need me to walk around to do this. Can anybody smell this?
What new chemicals are?
Anybody know how this smells? It smells like toasted marshmallows. Okay? And so it smells like toasted marshmallows because if you smell marshmallows that aren't toasted, they have one smell. If you toast them, they're going to have another smell. And that's because we're doing a chemical change to the outside portion of those marshmallows. And that's why we cook foods, is we're doing chemical change to either make them taste desirable or very often to kill off bacteria and other things that might make us sick. And those are chemical changes that are taking place. Next up, we are going to take another test tube. We're going to put some water into it. And we'll place the water over the flame. And as we heat the water here, notice that the water is beginning to boil. We're seeing some condensation forming on the upper portion of the test tube. So this here is boiling water. If we boil water, is this an example of a chemical change or is it a physical change? Boiling water. Again, ask yourself, do we have the same chemicals there or do we have different chemicals? Let's get your answers locked in, please. Count down. 5, 4, 3, 2, 1. This here is a physical change. A physical change because we started with water and we ended with water. We did change the phase of water. The water went from a liquid to a gas. But as we saw when it was condensing on the sides of the test tube up here, that condensed stuff there is water. We started with water. We ended with water. Next up here, looks like number 6. We are dissolving sugar in water. We're dissolving sugar in water. As we dissolve sugar in water, now the sugar is disappearing. Is this an example of a chemical change or a physical change? And we'll get our answers locked in, please. We'll count down. 5, 4, 3, 2, 1. Come on, there we go. This one here is a physical change. We started with sugar and water, and at the end we have sugar and water. How could we show that the sugar is still there?
You can evaporate the water.
Evaporate the water away would be one easy way. As we evaporate the water away, we should see that what we're left with is some sugar. Okay, next up, I am going to do this one right here. I'm simply burning natural gas. So again, as you're filling in your blanks, I am burning natural gas. Burning natural gas, is this an example of a chemical change or a physical change? Burning natural gas, chemical change or physical change? We'll give you 5 seconds to lock in an answer. We'll count down. 5, 4, 3, 2, 1. This here is a chemical change. We had different chemicals there at the end than we started with. It'd be great if we had the same chemicals at the end that we started with, because if they're the same, we'd have an endless supply of gasoline and natural gas and whatever. We could burn it forever. We can't. We know once we take it out of the ground, we burn it, it's gone. It changes into carbon dioxide and water. So again, we can't burn this forever. We eventually use up those resources. Next one is I have some magnesium. And with the magnesium, I'm going to go ahead and put this underneath the document camera. This one here now is going to burn rather brightly. Unfortunately, we have a little bit of extra light coming in, so you don't want to look at this directly when we do this. You want to kind of look at this at an angle. But again, this here is the magnesium metal as it burns. And we see now that that went out. If I were to come back and look at what's formed underneath here, it was kind of bright, but we see that we started off with kind of a white metal, or silverish metal. We now have a white, and this is reflecting some light, but we now have a white powder in here. So is this an example of a chemical change or a physical change? Chemical change or, whoops, sorry. Chemical change or physical change? We'll get our answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. This here is indeed a chemical change. Our first piece of evidence is a color change. Also, you can add this to your list of evidence of chemical change. Whenever you burn anything, we're looking at a chemical change. And we're down to our last one now. Last one, I have, let's see, solutions of sodium hydroxide and hydrochloric acid. Right here. I'm going to mix these together. There's my hydrochloric acid. Here's my sodium hydroxide. I'm going to take the temperature of each one of these. I have a temperature probe that I've hooked up to my laptop here. If I drop in the temperature probe into the hydrochloric acid and check its temperature, we see it is about 23.7 degrees Celsius. If I clean this off here and drop it into the sodium hydroxide, we see that it too is about 23.7 degrees Celsius. So I'm going to put this back into the hydrochloric acid. I am going to start collecting some data here so we can see what's happening to the temperature. There we go. And then I'm going to pour one into the other. Watch what happens to the temperature. And of course, as you feel this, how do you think it's going to feel? Yeah, definitely going to feel a lot warmer. So, is this one here completing it? Solutions of sodium hydroxide and hydrochloric acid are mixed. causing the temperature to go up? You can fill in the blank. It's causing it to go up. Is this an example of a chemical change or physical change? And we'll count down. 5, 4, 3, 2, 1. This is indeed a chemical change. This is our last piece of evidence for a chemical change. If you mix chemicals together and you see the temperature either go up or go down, that tells you that a chemical change has taken place. So again, mixing chemicals together, observing the temperature go up or go down, that is another piece of evidence for a chemical change. That's it for today, folks. Sorry I kept you over 20-some seconds.
Just like this stays the same. Okay, so like nothing is being.
Well, I should take care of it into a
Nothing
solid.
is being formed.
Or be your middle.
And I'll complete this table when I post it,
Like iced water, iced.
and I'll have my batteries charged by the next time we come to class.